Today we're going to talk about longitudinal stability, and mainly longitudinal static stability. We had a nice opening screen. If you see here all the pictures, my assistant warned me explicitly that he thought this was photoshopped. Well, probably yes. This lecture, he also asked me to warn you that this lecture is one of the harder ones, because we will not only look at longitudinal static stability in a qualitative way, but also in a quantitative way. So after this lecture, you should be able to calculate yourself the position, size of the tail, of the wing surface, the center of gravity, to make sure that the aircraft is longitudinally statically stable. You may have seen different configurations in terms of the tail of aircraft. You probably saw the T-tail or the tail which was mounted to the fuselage, even more exotic like twin tails or V-tails. And why is this, and what is the effect of such choices? And moreover, if we look at the total configuration of the aircraft, there are aircraft which have the standard configuration, like the normal aft tail. But you may have also seen a few which have a canard, so have a front tail and a wing aft. And there are free surface aircraft, Piaggio for instance, tandem wing, even some experimental design, tailless, flying wings. And there are many reasons to go for one configuration or the other, and many have to do with stability. And of course, for any configuration, you have to assure there's some level of longitudinal static stability. And therefore, we first have to look at what longitudinal static stability really means. So let's look at this aircraft flying in the cruise, which suddenly experiences a airflow upwards, turbulence, and there's an increase of angle of attack. The nose goes up. Then for a stable aircraft, for this positive delta alpha, we want a change in pitching moment, which brings the nose down again. So that's a negative pitching moment. And in this case, I've written the pitching moment coefficient to make sure that it's unitless and it works for all speeds and all altitudes. So the pitching moment, as a reaction to a positive delta alpha, the pitching moment should experience a change in the negative direction. The same goes if we go to the nose down example, for instance. We want for negative delta alpha, we want a positive pitching moment. In other words, the change should have a different sign in pitching moment than the change in angle of attack. And this we can also write in this way. Let's say that the delta Cm divided by delta alpha should be smaller than 0. And if we look at this for very small deviations, we write this with a normal d instead of the delta. So we say the small changes in pitching moment divided by the small changes in angle of attack should be less than 0. And this dCm d alpha is sometimes for shorthand also written as the Cm alpha. So it's the derivative of the pitching moment due to the angle of attack. And this is nothing else than dividing the change in pitching moment by the change in angle of attack. This is one of the 3 things you have to know before we can start the actual derivation of how we can make an aircraft longitudinal statically stable. The second thing you have to know is what happens at the tail surface of an aircraft. So if we look at a tail of a regular aircraft, if we see it here, then we can draw this more schematically by looking at the 2 wings here. We have the main wing in the front and we have the tail surface to the back. And often there is a little trim setting which causes the elevator to have a slightly upward direction, the tail surface to have a slightly upward direction. And this angle of incidence of the horizontal tail is called IH. So it's a tail surface setting set with the trim wheel by the pilot. And during our turbulence, this doesn't change. This is a constant. It is set by the pilot only to balance the forces, to make sure that the total moment around the center of gravity is 0 in the equilibrium, so that the aircraft will continue to fly at the same pitching angle, at the same angle of attack. If we then look at the angle of attack at the wing, this is the angle between the body axis and the speed, you might think that it's the same at the tail except for this angle of incidence. But this is not true. The wing generates a lot of lift. And this lift force is, if you zoom out, of course it's created by pressure of the distribution over the wing, but if you zoom out, the net effect is also that air is pushed down by the shape of this wing and by its angle of attack. And that means that the angle of attack at the tail is actually slightly less. The air is bent downwards a little, and this means that there is a different angle of attack at the tail. Of course, it can be increased again with this angle of incidence, the tail surface setting, but there's also a downwash which decreases it compared to the angle of attack, and this we normally write as epsilon, the downwash angle. If we write this mathematically, we can write this sum, which says the angle of attack of the horizontal tail surface is equal to the angle of attack of the whole aircraft, of the wing, plus the tail surface setting, the angle of incidence of the horizontal tail, but minus the downwash. And later, we will also want to see what the effect is of a change of angle of attack. And if the angle of attack suddenly changes, how will the horizontal tail surface angle of attack change? Well, we can derive this equation 2 alpha, and then we get this equation. The derivative of the tail angle of attack to the normal angle of attack is just the derivative of this equation. Well, the alpha becomes 1. The dd alpha of alpha is 1. The IH is a constant. It doesn't change due to alpha, so it becomes 0. And the downwash might change to angle of attack. So we simply write the change of downwash angle due to a change of angle of attack there, the d epsilon d alpha. In other words, the d alpha h d alpha is 1 minus d epsilon d alpha. And this is, for now, just a mathematical thing, what happens, what is when the angle of attack changes, but this is something we will use later when we look at the disturbance of the equilibrium. The third thing you have to know is a definition, and that's what we will use, and that there is one location for every surface, every wing surface, which is called the aerodynamic center. And it's the aerodynamic center is the position where the moment generated by all the aerodynamic forces around the airfoil, the moment does not change due to the angle of attack. So when there's a change in angle of attack, of course the lift will increase, but the moment will stay the same. Be aware this is not the same position as where if you would sum all the forces where the resulting force would be pulling on this wing, because it's specifically chosen for this reason of the moment that doesn't change, and due to an angle of attack. So if we get an extra angle of attack, the moment stays the same, but there will be an extra lift force. This we call the aerodynamic center, and that's very useful for our calculations. And you cannot write a simple force then instead of the wing. We have to write a force and a moment, but this is the moment around the aerodynamic center, and it will be constant for all angles of attack. So these are the three things which we will use in the derivation of our relation for the longitudinal static stability. So here we see schematically the same picture as we saw earlier on the situation in the tail in the lecture. We have a wing with a lift of the wing body, so everything of the aircraft without the tail. And then a bit further to the right, we have a little tail surface with LH indicating the lift of the horizontal tail. In the middle we have the center of gravity, CG, where the weight applies. And we have some dimensions indicated. LCG is the distance between the aerodynamic center of the wing and the center of gravity. And LH is the distance between the aerodynamic center of the wing and the aerodynamic center of the tail surface. We also have a moment in the wing, indicated in orange, the moment around the aerodynamic center, Remember, it doesn't change with the angle of attack, but it's also larger than 0. Actually, it's smaller than 0, but it's indicated here larger than 0, because we will, for our signs, we will always use this direction nose up as positive, and this is how we draw the moments. In reality, when there's positive lift, there is a negative moment. So MAC, as we have drawn it now, will be smaller than 0. But this is the direction which we use for all moments, and that's also how I draw it. So this is the total situation of this aircraft. And let's first look at equilibrium of forces. And this shows that if we look at the total forces up and down, that down we have the weight, and up we have the lift of the wing body, plus the lift of the horizontal tail surface. And this is in total the lift of the complete aircraft. So there, if these conditions are met, then we have a horizontal or a vertical forces equilibrium. And this is normally done by changing the angle of attack of the wing so that this total equation holds and that we are keeping our altitude. For the moment, we can do the same. We can write the total moment equation, which also has to be 0. So if we say the total of the moments, so this has to be an M, total has to be 0. Let's see what it is. It is, well, first of all, the moment around the aerodynamic center. And we can, because there's equilibrium of forces, we can also place this to the center of gravity. So if we look at the moment around the center of gravity, we can just use the moment around the aerodynamic center as if it was around the center of gravity, because there's an equilibrium of forces in the vertical direction. We can just displace the moment and it doesn't change, the number doesn't change. And then in the positive direction, we also have the lift of the wing body times the arm. We take the moment around the center of gravity, so it's LCG is the arm. And then, resulting in a negative moment, we have the lift of the horizontal tail times, and this is not just LH, but LH minus LCG, because that's the arm of this force, and that's this part of this side of the aircraft. So this is the total moment around the center of gravity, and we can simplify this slightly. So MAC remains MAC, but by taking away the brackets, LVB times LCG minus LH times small LH plus LH times LCG. The two minuses become a plus. Then we can see that these two are both multiplied with LCG, so we can also write this as MAC plus the lift of the wing body plus the lift of the horizontal tail times LCG minus the lift of the horizontal tail times little LH. We've seen that this, from our equation here, this is the same as the total lift. So let's write this as the total lift, and then we get our moment equation plus the lift times LCG minus LH times LH, and this has to be 0 to avoid the aircraft rotating. So we have adjusted the L to match the vertical force equilibrium. What we normally do then is to change the angle of incidence of the horizontal tail, so this angle, to make sure that we have a lift of the horizontal tail surface, which will make this moment 0, and this is what we call trimming the aircraft. So now we have an equilibrium of forces, an equilibrium of moments, and we have these equations which we can use. Especially this lower one is one that we can also use to then look at the stability. So what happens if there is a disturbance of this peaceful equilibrium while we're flying in our cruise flight? Well, we saw in the previous slide that therefore we use the moment coefficient. So let's first make this complete this complete equation for the total moment. Let's include that one. So let's use this total equation and make it unitless or dimensionless. So we know that the moment coefficient, Cm, is the moment divided by half rho v squared s times the average chord, which is the distance between the front leading edge and the aft leading edge of the wing, the average. Sometimes I write a little line above it because it's the average chord, but often I leave it out as well. I just write the C of chord. We have to remember it's the average chord. It's basically the span of the wing area divided by the span. That gives you the average chord. So by dividing the moment by half rho v squared sc, we get the moment coefficient. And this also goes for our equation. So let's fill our equation in and divide every part by half rho s squared. So we had the moment around the aerodynamic center. This has to be divided by half rho v squared sc. We also had our lift as a positive contributing lift times LCG has to be divided by half rho v squared sc, and also our negative contribution to the moment divided by half rho v squared sc. Well, let's see what we have as a result. We have MAC. This is nothing else than the aerodynamic center moment coefficient. And here we see that this coefficient we know. L divided by half rho v squared s, that is of course the CL of the aircraft. And what we are left over with is LCG divided by C, sort of unitless distance. And then here, well, this is slightly more complex. We cannot easily do the same trick because LH is CLH, is the lift coefficient as given for this surface. But of course, this was calculated for this specific area. So it's half rho v squared SH. So we have to write this here, CLH times half rho v squared S H times LH. And that has to be divided by half rho v squared SC. And we see that some things cancel out there easily, the half rho v squared, but not the S or the C. So what we're left over with is this part of the equation. And this we give a specific name because we have to write this a lot of time. We call this the tail volume, VH. It's a volume because it's a surface area times a length, but it's not a real volume. It's the surface area of the horizontal tail times the arm of the horizontal tail divided by SC of the wing. But it gives our total equation and makes it much more readable by using all these coefficients. Is CMAC plus CL times LCG over C minus CLH times the tail volume, VH. And this is basically the same equation as we've written on the previous slide. It's the one we had below here. The total moment and lift. But now everything is made unitless, dimensionless, in coefficients. But in essence, it says the same thing. Now, what we said that for stability, this moment, this change in moment coefficient due to a change in angle of attack had to be negative. The two things had to be have to have an opposite sign, the change in moment and change in angle of attack. So the DCM, the alpha, had to be negative. So we will use this equation to calculate the derivative of it due to alpha. So we have this equation, Cm is Cm aerodynamic center plus Cl times LCG over C minus CLH times VH. And then we have to calculate the derivative to alpha. So to get the DCM d alpha, because that's apparently our parameter which has to be negative for longitudinal static stability. Well, the first thing we do, we have to derive the moment coefficient in the aerodynamic center due to alpha. Well, the derivative to alpha means the change due to a change in alpha. Well, the definition for aerodynamic center was that this was 0. It's constant for all angles of attack, so the derivative to alpha is 0. Here, for the lift, this is not true. If we change the angle of attack, the lift coefficient will increase. So it will be dCl d alpha for now. LCG, the dimensions of the aircraft do not change due to an angle of attack. So this is just a constant with which we multiply. And here we have to write the change in lift coefficient of the tail surface due to change of angle of attack. And VH is again the dimensions of the aircraft will remain constant. So we are nearly there. These coefficients, this is easily obtained. The DCL, the alpha, you will just go to your aerodynamics guy and he will give you the lift curve and he will say, okay, normally you're flying in this region where CL due to alpha change in a linear fashion, and you will just have to use the steepness, which we often call A. A is simply the DCL, the alpha, but then the constant part. The A, he will give you this number for the airfoil and you can just use it. So you can say, we can write this Cm alpha is the same thing as DCM d alpha. So we can leave out the 0 and we say basically A times LCG divided by C. And this is just a figure your aerodynamics people can give you for specific airfoil. Well, the same, of course, is true for the horizontal tail. They will also give it to you for the horizontal tail, but they will then give it to you for the angle of attack of the horizontal tail. And then you will get the A of the tail, the AT. But now there's a problem because we can get this number, but we need a different number. We need the DCL, the alpha. Well, what we can do, of course, is say we can multiply the DCL, the alpha, by d alpha h divided by d alpha h, because that's 1. The change of itself due to itself is always 1. It's also, if you look at it in deltas, it's the denominator and the low part of the fraction is the same, so it's multiplied by 1. This we can also write as DCL d alpha h times, oh not this, times d alpha h d alpha. And this we know, we've calculated this before. This was 1 minus d epsilon d alpha, and this is simply the AT, the steepness of the curve for the tail. In other words, we can write this as the AT times 1 minus the epsilon the alpha times VH. And that's this trick. But just multiplying it by 1 and then writing it in a different way. It's also this way, by the way, you might also recognize as the chain rule for derivation. So here we have the CM alpha, and this had to be smaller than 0. It had to be negative for stability. So let's see what this means. This means that if we move this to the other side, you basically say that the A LCG divided by C has to be smaller than the AT 1 minus the epsilon, the alpha times VH. What we've done here, we've moved this part to the other side of the equation. You could also say that when this is smaller, because they're all positive numbers, if this is smaller than this part, then the total result will be negative. And if we then divide by A on the left and right side, we get our, oh, this doesn't do what I expected it to do. So like this. We divide by A on the left and the right side, and then we get this equation. I'm going to write it here. We get then here AT divided by A, and this is the total definition of longitudinal static stability, that the center of gravity, the length between the distance between the aerodynamic center and center of gravity divided by the chord has to be smaller than this equation. These are all numbers you can get for specific choice of airfoils for your surfaces. And here in this side of the equation, this VH is basically a design parameter. Remember, this was SH times LH divided by SC, the tail volume. And this is basically your aircraft configuration in one number. If you choose a certain distance to the tail or a certain size of your tail, this will influence this VH and therefore influence your stability. And this whole side of the equation, if your center of gravity is equal to this, so if we have it equal, then we call the center of gravity position, we call this a neutral point. So the neutral point means it's equal to this, and because then the CM alpha is 0, and it means there's neutral static stability. You can therefore also say that the center of gravity has to be before the neutral point, because it has to be smaller. This distance has to be small, so this center of gravity, let's see, this distance has to be small, so the center of gravity has to move in this direction to make it more stable, might even be negative. The more forward, more stable it is. And there is a position here, the neutral point, on which you're on the verge of instability, and if you go in the other direction, you will be unstable with your center of gravity if you move it here. And therefore the distance between your actual center of gravity and the neutral point is your margin, and this is called your static margin. And it shows the margin you still have in the aircraft. So if you're ever in an aircraft and the captain says, oh, we've done something wrong with our weight imbalance and we're nearly unstable, it's best to all run to the front of the aircraft to move the center of gravity forward and ensure stability. So we have derived this first equation here, the center, the position of the center of gravity and how it influences the CM alpha. And you see here the result of our equation. And we've also said that if you want to be statically stable, then CM alpha has to be 0. So then we get this neutral point. The center of gravity is then in the neutral point. And normally we want the CM alpha to be less than 0, which means that the center of gravity, or the LCG, this arm, has to be less. So in other words, the center of gravity has always has always to move forward for more stability. It has to be before the neutral point. And the distance between these two positions is what we call the static margin. It's the distance between the center of gravity where it actually is and the position where it should be in case of neutral stability. So as long as we have a positive static margin, we have a positive aircraft. As soon as we get our center of gravity beyond the neutral point, then we will get an unstable situation. Well, this is of course true for a conventional configuration like we have here. But of course there are also aircraft which have a less conventional configuration, for instance the Canard. And the Canard aircraft has it reversed. And of course a nice question now would be, how does this work for this type of aircraft? And this will be a nice thing to try at home, to do the same thing that I just did. Maybe you have to watch it another time or maybe once or twice to see what we really did, the steps that we did there. But to summarize it, the idea is that you first make your moment equation for this aircraft. Now we have a lift of the Canard here and we have the lift of the wing body there, so on the aft side. And then you have to derive first make it dimensionless, unitless, and then derive it to the angle of attack. And then you have to say the Cm alpha has to be negative, because also for Canard you want the effect that the reaction to a positive deviation alpha is a negative moment coefficient. So that stays the same, but of course some dimensions are different. And one thing that is different is that in a way the Canard is easier, because you can ignore the downwash of the Canard surface on the wing. And there are a number of reasons for this. One is that the Canard is very small, and the other one is that it's a symmetrical airfoil in general, which is also the reason why we did not have a moment around the aerodynamic center of the tail surface or Canard surface. It's a symmetrical airfoil, and therefore it will not generate a lot of lift, and it will not have a lot of downwash, because downwash was the result of lift. And the downwash of this wing clearly does not affect the Canard surface. So in a way it's even easier. But try it and see what the criteria are for the center of gravity location for a Canard aircraft. Good luck with that.